Dear student, hope that all of you are well, and I welcome you once again to the lecture series 3, in which we'll once again discuss the remaining some parts of the chapter power series solution of differential equation and special functions. And in this lecture, the topics we'll learn are first Legendre polynomials, then general solutions of Legendre differential equation, and after that generating function for the Legendre polynomials p n x, and followed by orthogonality of Legendre polynomials, and then some useful relations regarding p n x, that is regarding the Legendre polynomials, and after that recurrence formulae for p and x, and finally some relations using recurrence formulae for p and x. That is, there are some relations which will depend on different recurrence relations of p and x. However, before begin this lecture, we have to recapitulate the Legendre differential equations and its two solutions, which we have discussed in the lecture series 2. So first, the Legendre differential equation which is written here, it is 1 minus x squared d2y by dx squared minus 2x dy by dx plus n into n plus 1 into y, that is equal to 0. You know that here n is a constant, and this differential equation has two solutions, as we learned it in our previous lecture, that one of them is y1, which is written as a0 x to the power n minus n into n minus 1 by 2 into 2n minus 1 into x to the power n minus 2 minus n into n minus 1 into n minus 2 into n minus 3 by 2 into 4 into 2n minus 1 2n minus 3 into x to the power n minus 4 minus etc. There are other some terms, but we write here up to these terms. Okay, and then the second one is a0 into x to the power minus n minus 1 plus n into n plus 2 by 2 into 2n plus 3 x to the power minus n minus 3 plus n plus 1 into n minus 2 into n minus 3 into n minus 4 by 2 into 4 into 2n plus 3 into 2n plus 5 plus other terms. So we have two solutions of Legendre differential equation. Now come to the point that the topic that are Legendre polynomials, which is written as p n x. Now, if one thing you see here, that here a0 these a0s are constants, arbitrary constants. So if you consider that the arbitrary constant a0 is written in this fashion, if you consider or if you think that a0 is written as 1 into 3 into 5, that is the last term of the series will be 1 here, then 2, that means 2n minus 1. So it ends as the last term as 2n minus 1 by factorial n, where n is a positive integer as we discussed it earlier, and then the solution of the first solution, that means this solution y1 is equal to this solution will be in the form that y is equal to p n x, and this solution is called the Legendre polynomials, and therefore we can write the first solution, that is y1 is equal to p n x. So here we write that p n x is equal to 1 into 3 into 5 dot 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 into 2n minus 1 by n factorial into x to the power n minus n into n minus 1 by 2 into 2n minus 1 into x to the power n minus 2 plus other terms. Here I have written plus, so no matter, all terms will be negative. So actually this is actually negative sign. So Pn is called the Legendre function of the first kind. and in this case Pn x is called the Legendre function of first kind. You should remember that any solution of Legendre differential equation in the form Pnx is called the Legendre function. However, if the arbitrary constant a0 is taken as a0 is equal to n factorial by 1 into 2 into 3 etc. 2n plus 1, where n is a positive integer. If you take a0 as this, then the second solution of y, that means the solution, this solution y2 is equal to a0, this solution will have the form qn is equal to n factorial into 1 into 3 into 5 2n plus 1. I have written is as qn. So this into x to the power minus n minus 1 plus n plus 1 into n plus 2 by 2 into 2n plus 3 into x to the power minus n minus 3 plus other terms. And in this case qn is called the Legendre function of second kind as it has come from the second solution, so it is so called, that is the Legendre function of second kind. So here the Legendre equation can also be written in generally as d dx of 1 minus x squared dy by dx plus n into n plus 1 into y is equal to 0. You can calculate this. If you calculate this, you will get the familiar Legendre differential equation, that is 1 minus x squared d2 y by dx square minus 2x dy by dx plus n into n plus 1 into y is equal to 0. So now come to the another topic, which is the general solution of Legendre equation. So we have two solutions of Legendre differential equation and which are called the Legendre polynomials of first kind and second kind, and they are denoted as Pnx and Qnx as we saw in our previous topic. So Pn and Qn are the two solutions of Legendre polynomial equations, and these two solutions are independent, and then the Legendre equation has the general solution, which can be written as y is equal to a into Pnx plus b into Qnx. That is the linear combination of these two independent solutions. And here remember that a and b are two arbitrary constants. And you also note that the solution Pnx, that is we come to the previous pages, which is here. Pnx is equal to 1 3 5 these and this term, and you can easily understand from these relations that Pnx has finite terms, that is it will have finite terms. But in case of Qnx, which is written here, that is Qn is equal to this, and this term will have infinite number of terms. So since these two terms, the first one has finite terms and the second one, that is Qn, has infinite terms. So first one, that is Pnx, is rather important, and in more cases we will use frequently the first solution Pnx, that is the first polynomials. However, now we come to the second another topic, which is the generating function of Pnx. The term 1 minus 2xt plus t squared to the power minus half, it is written as n is equal to 0 to infinity tn Pnx, and this term is called the generating function for Pnx, because you can carry out or you can compute the Legendre solution of Legendre differential equation with this function, with this term, or this better it is called this function, and thus it is called the generating function of Pnx. And you can write it as in this fashion. So we will try to prove this whether this is the generating function. That means the solution of Legendre differential equation of first kind we will discuss, or we will use the first one here. So this function is chosen in such a way that the solution of first kind of Legendre differential equation can be derived from this function. Now, to do this, first we just look at the binomial expansion of a function that is written as 1 minus y to the power minus, and it can be written as first 1, then plus n into this power n into y, then plus n into n plus 1 by 1 into 2 into y square, and the next term will be n into n plus 1 into n plus 2 by 1 into 3 2 into 3 into y cube plus other terms. You can see this binomial expansion in through your website, through any website. So actually this binomial expansion of this function will be in this manner. So however, this function can be written in this fashion, in which y can be written as minus 2x minus of 2xt minus t square. Okay, because if you take minus as common term, then the residual part, or the rest part will be 2xt minus t square. So y can be written as y can be compared with these terms, second two terms. So and here the power is minus of, that is n is, if you compare these two terms, then you will have n is equal to half. So taking n is equal to half in this binomial expansion, you will have 1 minus y to the power minus half, that is equal to 1 plus n is equal to half here. So here you will substitute half in case of n. So that will be half into y, then plus n is equal to half here, and n plus 1 is equal to half plus 1, that means 3 by 2 here, by y square, and here will be 1 into 2 plus n is, in this term n is half into n plus 1 is 3 by 2, and then n plus 2 is 5 by 2, and here 1 2 3 into y cube plus other terms. So after simplification, you will have 1 plus 1 by y, half 1 plus half y plus 1, you can write here as 1 into 3 into pi square by this 2, and this 2 will come here and here. So you can write here 2 into 4 plus, in the same fashion you can write 1 into 3 into 5 in here, and here you will write 2 into 4 into 6 into y cube plus other terms. In this way, the last term will be, see, this is very important. See here, you are writing in here the series is 1 3 5. So it is the first term, the second term, so this is the after that third term. So actually here, and you see that in this case n is 3, so this term is 2n minus 1. If you the last term will be 2n minus 1, okay, because the last term here is 5, so 5 is nothing but 2 into 3 minus 1, that is 2n minus 1, so last term will be 2n minus 1, and here 2 4 6, so this is actually n is here 3, so the last term is 3 into 2, that means 2 into n, so the last term will be 2 4 6 etc. into 2n into y to the n plus other terms. So it is, I hope that it is clear to you. Now using y is equal to, as I said before, that y is equal to here 2xt minus t square. So we have from this relation y is equal to t as a common term, t into 2x minus t. So if you substitute the value of y in this series, then what you will have? You will have 1 minus 2x t minus t square to the power minus f, that is equal to 1 plus what was the next term? Next term was half into y. So here half is here, and y means t into 2x minus t. So it is t by 2 into 2x minus t, and the next term was 1 into 3 by 2 into 4 into y square. So I have written here the same thing, 1 into 3 by 2 into 4 into y square means t square into 2x minus t its whole square. And in this way, the third term will be 1 into 3 into 5 into here, 1 into 3 into 5, 2 into 4 into 6 y cube. So you write here, we write here 1 into 3 into 5 by 4, 2 into 4 into 6 into t cube into 2x minus t whole cube plus etc. other terms, and plus the final term. The final term is 1 into 3 into 5 etc. into 2n minus 1. You can see, you can also see from here 1, 3, 5, 2n minus 1, and in this way 2, 4, 6, 2n into yn. So here I have written this is that written that 1 into 3 into 5 etc. 2n minus 1, and here 2 into 4 into 6 etc. to 2n and y to the power n, and here is y is t into 2x1 2xt, so 2x minus t, so you write here t to the power n. From here t to the power n is written here, and 2 into 2x minus t to the power n. So we can write that this term, the binomial expansion of 1 minus 2xt minus t square to the power minus r, that is nothing but 1 minus 2xt plus t square, that is equal to this. So now here the last term, you see that the last term has a term which is 2x minus t to the power n. Now we have to expand this term also. So the general form of expanding this type of function is a plus b. Here a is 2x and b is minus t. To the power n is equal to all terms of this series. That is, it can be written as NCR a to the power n minus r b to the power r. So you write here that 2x minus t to the power n is equal to, and here r will be started from 0 to other higher terms. So here you write NCR, that means you will start from 0, r is equal to 0. So NC r is equal to 0 here, and a is, what is a? A is 2x. So you write here 2x to the power n minus r is 0 here, so 2x to the power n into b is equal to minus t here, so minus t to the power 0, because you take for the first term as n is r is equal to 0. For the second term, what is the second term? What will be the second term? You write here plus, the second term will be, in this case r will be 1, so nc1. You write here nc1, and then a means 2x, here 2x to the power n minus r, that means n minus 1. So you write here 2x into n minus 1 into t, b is equal to minus t to the power r is 1 here, so minus 1 minus t to the power 1. And the very next term will be plus, in this case we have r is equal to 2, so n in nc2, and a is 2x to the power r is 2 here, so n minus 2 into minus t, as b is minus t to the power r means here r is equal to 2 minus other terms, that is equal to, now come to the next line here, you know that this term nc0, that means the value of nc0 is equal to n factorial by 0 factorial into n minus 0 factorial, so that is n factorial by n factorial, that means 1. So you get here this term is equal to 1, and this is equal to 2x to the power n, and t to the 0, that is 1. So first term is 2x to the power n, and the next term, the second term is, and the negative sign arises from this sign, so negative sign is here, and you write it nc1 is here, then 2x to the power n minus 1, it is also written here, and the third term is t to the power 1, I have also written here. And the next term, we will simplify these terms nc1 in some other steps, after some steps. So we write it as it is. Now the third term is nc2, 2x to the power n minus 2, and t square, and other terms. So from equation I have written this expansion, that is the binomial expansion of this term. This is, I have written this as equation 1. Now we are interested to substitute the value of 2xt minus 2x minus t to the power n here in this equation. So we write here 1 minus 2xt minus t square. I can write it also in this fashion. So 1 minus 2xt minus t square to the power minus r, that is equal to write all other terms first all other these all terms up to this. So I have written that 1 plus half t into 2x minus t plus 1 into 3 2 into 4 t square 2x minus t whole square plus 1 into 3 into 5 by 2 into 4 into 6 t cube 2x minus t to whole cube plus etc. plus the final term. Final term has the constant term, that means this term 1 into 3 into 5 etc. 2n minus 1 by 2 into 4 into 6 etc. to 2n into t to the power n. I write this whole term except this term first. So I have written here here the last term 1 3 5 2n minus 1 by 2 4 6 etc. 2n into t to the power n. Now into the binomial expansion of x 2x minus t to the power n as we obtained here. So I have written here 2x to the power from this line, from this here, right? Just this the value of this 2x minus t to the power n. So 2x to the power n minus nc1 2x, that only right here this line. So here nc1 2x to the power n minus 1 into t1 plus nc2 2x to the power n minus 2 into t square minus other terms. So just simplify here. It is equal to 1 plus first 1, 2 and 3 terms. I have written here first term, second term and third term. So there is no difficulty to understand it. And the last term, the last term, I have written here 1 into 3 into 5, 2n minus 1 by 2 into 4 into 6, etc. 2n into just I just multiply t to the power n to all these terms. So here 2x to the power n into t to the power n minus nc1 2x to the n minus 1. T to the power n is here and here is t to the power n, so it will be t to the power n plus 1, and the term after that is equal to nc2 2x to the power n t to the power here t square and here t to the power n, so t to the power n plus 2 and all other terms. I have written it as equation number 2. So now collecting the coefficients of t to the power n. Now collecting the coefficients of the binomial expansion of this as we obtained as this, and now we are interested to collect the coefficients of t to the power n from this equation number 2, and you are very and you see that only t to the power n terms contain the t to the power n, the term t to the power n contains only the last term. T to the power n contains only these last terms. So we only concentrate on the last term, that is this term. So now we wish to collect the coefficient of t to the power n. So from the first term, so right here this term first, so 1 into 3 into 5 etc. 2n minus 1 by 2 4 6 etc. 2n, and if you and for the first term 2x to the power n will come here, and since it is t to the power n, so the first term will be 1 3 5 1 3 5 this, and for the second term, this is the second term here. See, you see that t to the power n plus 1. So if you wish to collect the coefficient of t to the power n, so you have to replace here n by n minus 1. So if you replace n by n minus 1, what we will have here, you will have t to the power n minus 1 and then plus 1, so t to the power n. So this will be the coefficient of t to the power n. So we write here first 1 3 5 2n. Remember that n is replaced by n minus 1, so you will have from this term 2n minus 2 and then another minus 1, so it will be 2n minus 3, and here 2 4 6 and it will be 2n minus 2 as n is replaced by 1. So 2 into n minus 1, that means 2n minus 2. So I have written here 2n minus 2, and then x to the power n is replaced by n minus 2x to the power, since you replaced here n is n by n plus, sorry, n minus 2. So in this case n should be replaced by n minus 2. So what is there, t to the power n? So the next term will be 2x to the power n minus, here you replace n 2x to the power, here you write a 2x to the power n, and n is replaced by here you write that n is replaced by n minus 1, and here what was that, 2x to the third, second term was 2x to the power n minus 2, so no problem. And then since n is replaced by n minus 1, so it will be n minus 1 bar into c1. Then I have just, since I have replaced n by n minus 1, so here n minus 1 and then another minus 1, so it will be n minus 2. So I have written a 2x to the power n minus 2, and then n is replaced by n minus 1, so n minus 1 into c1, and this is the second term. I have written here also n is replaced by n minus 1, and then for the third term, here if you wish to collect the coefficient of t to the power n, so you have to replace n by n minus 2, and then 2x to the power n should be replaced by n minus 2, so 2x to the power 2n minus 2 minus 2, so that will be 2x to the power n minus 4. So and writing all the these terms 1 3 5, so I have written here 1 3 5 etc. The last term is here 2n minus 1, so as you replaced n by n minus 2, so from this you will have 2n minus 4 minus 1, that is equal to 2n minus 5, and here in this series the last term will be 2n minus, as n is replaced by minus 2, so it will be 2n minus 4, and here 2x to the power n minus 4, and then n is replaced by n minus 2, so n minus 2 c2 another term. So I hope that you will understand, and here also written as n is equal to n minus 2. We just put it to this last term, this term, third term. So and plus other terms also. So we get, after collecting the coefficient to the power n, the series as this, and now it is equal to, now we wish to, this is the common term 1 3 5, if we wish to, no, here we just simplify this in this line, so it is 1 3 5 2n minus 1 2 4 6 etc. 2n into 2 to the power, I just write it as 2 to the power n x to the power n, and then minus 1 3 5 2n minus 3 2 4 6 2n minus 2 2 to the power n minus 2 and x to the power n minus 2, you can write from this, and this term just expand this will be the factorial, first the factorial of these pi, the factorial of these minus the factorial of these minus this. I have written here, that is first will be the factorial n minus 1, and then 1 factorial by n minus 1, and this one will subtract from this, so n minus 2 factorial. Okay, then the third term 1 3 5 2n minus 5 by 2 4 6 etc. 2n minus 4 2 to the power, you can write this as this term as 2 to the power n minus 4 into n minus 4, and this term as n minus 2 factorial, you write here n minus 2 factorial by 2 factorial is written here into n minus 2 minus these 2, so n minus 4 factorial, and all other terms. So here you can understand that these two terms in this case, in this line, the two terms is just written for our simple only changes are done in these two terms, last two terms. So this can be written as 1 3 5 etc. 2n minus 1, and you can write it as this is as 1 into 2, then 2 into 2, then 3 into 2, then n into 2. So you can here 2 is multiplied twice in this series by n times. So you write a 2 to the power n, and the rest parts will be 1 into 2 into 3 etc. to n, because you this what can be written from this series. This is 1 into 2, and this is 2 into 2, this is 3 into 2, that etc. It is equal to n into 2. So 2 is multiplied n times, that means 2 to the power n. So I write here 2 to the power n, and the rest part will be 1 into 2 into 3 etc. 2 per second, and here 2 to the power n into x to the power 9 to the power n, and then minus 1 3 5 this series. And what can be written from this series? If you think that here 2 is multiplied, so 1 into 2, this is 2 into 2, this is 3 into 2, and in this fashion what we'll have from this is equal to nothing but 2 into n minus 1. So here 2 is multiplied to n minus 1 times. So I write here just write at 2 to the power n minus 1. It should be 2 to the power n minus 1, but I write here n minus 2. So n should be 2 should be multiplied here, should be multiplied to 2. You understand? Here, if from this series, if we wish, if you think that 2 is multiplied to n minus 1 times, okay, here you take 2 as common, so n minus 1. So 2 will be multiplied to n minus 1 times. So here it should be 2 to the power n minus 1. So I write here 2 to the power n minus 2. So another 2 should be multiplied here. So such that this term will be 2 to the power n minus 1. And from this series, what will be there? 1 into 2 into 3 etc. to n minus 1. And I also and this term, okay, this term no problem, it is written as usual, and I multiply here another term n. So I have to multiply here also another term n, that will cancel each other, and then I am just multiplying this series by 2n minus 1. So I have to divide by 2n minus 1 also, and then just simplify this term. So this term is nothing but if you simplify this, so first will be n minus what is so no from the second term, what will be the n minus 1 factorial, then n minus 2 factorial. I have written here n minus 1 into n minus 2 factorial, and here n minus 2 factorial plus the third term. Now come here for the third term. The term was 1 into 3, 1 into 3 into 5 etc. in this fashion, 2n minus 5, okay. And then come here 1 into 2, 2 into 2, 3 into 2 in this fashion. If you take 2 as common term, so it will be 2 into n minus 2. So 2 is multiplied here to n minus 2 terms. So I can write here 2 to the power n minus 2. Actually it should be 2 to the power n minus 2, but I write here 2 to the power n minus 4. So if I write 2 to the power n minus 4 as it was done in the first case, in this case, so I have to multiply this term as 2 to the power 2 square, that means 4. So such that it will be 2 to the power n minus 2. Okay, you understand, I hope. And then here and here this term what will be 1 3 5 etc. n minus 2. But I additionally multiply this series by n minus 1 into n. As I multiply this n minus 1 into n, so I have to multiply here also in the denominator, that is in the numerator, that is n into n minus 1. So it will cancel out, and then another two terms, addition 2 terms I have written here, that 2n minus 3 into 2n minus 1. So I have to divide it also, 2n minus 3 into 2n minus 1. Okay, and just then simplify this term. What is this term? What will be this term? This term is n minus 2 factorial. That means n minus 2 you can write it as n minus 2, n minus 3, and n minus 4 factorial. You can leave it here, and in the denominator it will be 2 into n minus 4 factors, so it means 2 n going to cancel out. So what you will have from the first term, that is these. So 1 into 3, you can 1 into 3 into 5 etc. 2n minus 1 by, if you cancel out 2 over n and 2 over n will cancel out. So 1, 3, 5 2n minus 1 by 1 into 2 into 3 etc. to n. So it is nothing but n factorial. So you write here 1 into 3 into 5 etc. to n minus 1 by n factorial. What is the residual part? That is equal to x to the power n, and I have written it as the common term. So from these, if we look at these, so we will have 1 into 3 into 5 2n minus 3, and the last term will be 2n minus 1. So 2n minus 1. Okay, so it is okay. 1, 3, 5 2n minus 1, it is the common term by n factorial. N factorial means you will see here n 1 into 2 into 3 etc. towards n minus 1, and the next term is just take n from here. So it will be n factorial. So you write here factorial n, and the rest term will be, you cancel this term and this term. Okay, and now what are the residual part? That is equal to n is from here and n minus 1 is from here. So you write n into n minus 1, and 2n minus 1 is from here, 2n minus 1. So you write here 2n minus 1, and another 2, that is this 2. This 2 is written here. So second term is n into n minus 1 by 2 into 2n minus 1, and here from here x to the power n minus 2. So I write here x to the power n minus 2. And from the third term, what is there? From the third term, you see here that 1 into 3 into 5 etc. towards n. So it is n factorial. So I write here n factorial. Okay, no problem. And from here 1 into 3 into 5 2n minus 1. The very next term is 2n minus 3, and the last term is 2n minus 1 in this series. So you write here as the common term, no problem. And then you just cancel out this term and this term, and then what are the residual parts? Residual terms, that are n into n minus 1 is written first, and then n, you cancel out from this term and this term. So the rest terms are n minus 2 into n minus 3. So you write here n minus 2 into n minus 3, and in here 2 to the square is left here, and 2 is also left here. So here you can write 2 into 4. Okay, no problem. And then 2n minus 1 is first right here, and then 2n minus 3, and x to the power n minus 4, and all other terms. So we finally obtain this relation, and you see that this is nothing but the polynomial of the first kind, that is Pnx. So we finally we get that Pnx is derived, that is Pnx is derived from which term? Pnx is derived from the term 1 minus 2xt plus t square to the 1 minus half, and so it is called the generating function of Pnx. Okay, I hope that you understand, and just you practice in your home. And now we come to the topic orthogonality of Legendre polynomials, and you will see that the Legendre polynomials is nothing but a set of orthogonal functions in the interval minus 1 to 1. And let us prove it. The statement, what is the statement? The statement is Legendre polynomial, that is Pnx, and this Pnx is nothing but a set of orthogonal functions, in the interval minus 1 to plus 1, and we are here to prove it. We know that Pnx. You know that the solution of Legendre differential equation is, one of the solution is y, and which can also be written as Pnx, that is the Legendre polynomials, and it is the first kind. And since the first solution has finite terms, so it is very often used in our practical cases. And so you write here Pnx is equal to, let that Pnx is equal to y, and it is the solution of Legendre equation, the familiar Legendre equation, which is written here, also written here, and you are very familiar with this equation. Okay, and now just that means this is the Legendre equation for a function y, which is written as Pnx, the polynomial of x. And if you consider that another function, another variable z, which can be written as Pmx, that is another differential equation you are interesting to write, which is a function of in which z is a function of x, and the equation can be written in this fashion, that is 1 minus x square d2z by dx square minus 2x dz by dx plus m into m plus 1 into z is equal to 0, where m is a constant, and this Legendre equation will have the solution z, and you write z is equal to the polynomial of Pmx. Okay, and in this case, so we see here two Legendre equations, 1 and 2, and which are solutions z from from here we will find the solution for z, and from here we will find the solution of y, and these two solutions are Pnx and here Pmx. So now multiplying this equation by z and this equation by y. So what will be that? 1 minus x square z into d2y by dx square minus 2xz dy by z plus n into n plus 1 into zy, and multiplying this equation by y. So 1 minus x square d2z by dx square minus 2 x and then y and dz by dx plus m into m plus y, and final term will be yz, that is equal to 0. Now substituting the second one after being multiplying by y from the first one after being multiplying by z, what we will have, this is the common term 1 minus x square, from the first term z into d2y by dx square, and from this y into d2z by dx square, then minus 2x is a common term. So from here you will have z into dy by dx, and from this you will have y into dz by dx plus n into m plus 1 minus m into m plus 1 into yz, that is equal to 0. And then just simplify this 1 minus x square z into d2y by dx square minus y d2z by dx square, this term is written here, and from here 2x z into dy by dx minus y into dz by dx plus from here just simplify this n square, and from here n minus m square minus m into yz. So here the first two terms remains as it was, and from the second, from here you can write a from after doing simplification n minus m from the first this n and this m, so you will have n minus m plus n minus m, and from these two terms n plus 1 into n minus 1. So from the whole terms n minus m is a common term, so I have written here, and rest terms are n plus m plus 1. Just simplify it, you will get this term. It is not very difficult. It can be achieved. It can be find out very easily. So we obtain after doing simplification the above equation, we will have this, and I write here it is as equation 3. So so this can be written. This can also be written as d dx of 1 minus x square z into dy by dx minus y into dz by dx. Just differentiate these terms, you will get the first two terms, and then n minus m into n plus m plus 1 into yz, that is equal to 0. So this is actually, it would be better if I denote it as equation 4. However, I have written it as equation number 3, but we will write it as equation 4. Now integrating this equation with respect to x from minus n to plus 1, minus 1 to plus 1, what we will have that 1 minus x square, then z into dy by dx minus y into dz by dx. So just after being, you can write the second line from this line, that d of this term plus n minus n, this yz into dx. If you integrate this integration of d of 1 minus x square into z or another and the rest terms into the this, okay, integration sign is here and d into 1 minus x square and the rest term plus integration of n minus this term right here and yz and dx. So after doing integration, after completion of the integration, you will have 1 minus x square z as it is d of this. So 1 minus x square z into dy by dx minus y dz by dx. It is from minus 1 to plus 1 plus n minus 1 into n plus m plus 1 minus 1 to plus 1 yz dx, that is equal to 0. So if you write the values of x plus 1 to minus 1 in this equation, that for case of x, if plus 1 is taken here, it is 0, and if minus 1 is taken here, also it is 0. So first term is nothing but 0. And from the second term, you will have n minus 1 into n plus m plus 1 minus 1 to plus 1 yz dz, that is equal to 0. Or since this term is not is equal to 0, so you write here minus 1 to plus 1 yz dx is equal to 0. That means y is nothing but pmx and z is nothing but pmx. Dx is equal to 0. It is integral 1 minus 1 to plus 1. As we write that pmx is nothing but y, the solution y, and pmx is the solution of z for z. So finally we get, and remember that m is not equal to n. So finally we get that minus 1 to plus 1 pmx dx is equal to 0, and this is called the orthogonality function of Legendre polynomials, and obviously the condition should be n not equal to n. So then we come here the next topics, some useful relations using the generating functions. As you saw earlier that the generating function of the Legendre polynomial is written in this fashion, that is equal to n equal to infinity to the power n pn of x, that is equal to 1 minus 2xt plus t square to the power minus half. Just write this term as that means you write here 1 minus 2xt t square to the minus half, that is equal to, you just write here different values of n, but we will have first term t to the power 0, that means 1, and p0 of x, then the second term will be t to the power n, that means t, and then p1x, and the next term will be t square into p2x, etc., and the last term will be t to the power n pnx. And also you write this term as, I write this as equation number 2 and this is equation number 1. And also you have 1 minus 2xt plus t square to the minus half. It can be written as 1. First write, think of this term, that 1 minus of 1 minus of 2xt minus t square. And if you take t as a common term, then what is that? That is 1 minus of t into 2x minus t. So this is nothing but 1 minus of 2t into 2x minus t to the minus half. And if we expand this, it will have 1 plus, first this plus will come here, half is here, and then from here 2x minus t plus other terms. I am not interested to write other terms, only these terms. I write here only these terms. Now comparing this equation number 3 to equation number this equation 3, and just compare 2 and 3, these two terms. What we will have? We will have here the coefficient of p0x. Here the coefficient of what will you will have? No, the coefficient of t to the power 0. Here the coefficient of t to the power 0 is 1, and here the coefficient of t to the power 0 is p0x. So you can write very straightforward from this comparison that p0x is equal to 1, and then from the next term, from this term and this term, just compare the coefficient of t. You will have p1x, that will be equal to half into 2x minus t. However, in this relation, that means here if you write in this relation as x is equal to 1, what will you will have in this relation? That is equation number 2. You are interested to replace x by 1. Then what we will have? First I write at the second right hand side p0 1 plus other terms plus pn of 1. That will be what we will have from these 1 minus 2t from here plus t square to the minus half, that is equal to 1 minus t to the power 1 minus t whole square, and here is minus half, so it will be 1 minus t to the minus half 1, and if we expand it, it will get 1 plus t square etc plus t to the power n at the last term. So you can here you can also compare the coefficients of t to the power n. If you compare the coefficient of t to the power n from both sides, we will have pn1 that is equal to pn1 that is equal to 1 from here. So pn1 is the coefficient of t to the power in the series written here, and that means t plus t 1 plus t plus t square plus etc t to the power n, and that is nothing but 1. The coefficient of t to the power n is here is 1, so pn1 is equal to 1. Similarly, using x is equal to minus 1 in equation here 2, what we will have, you will have if you wish to replace x by minus 1, so from this term you will have 1 plus t to the power minus half, and this term will be the same. So here you write these as p of p0 minus 1 plus plus other terms t to the power n, pn of minus 1 that is equal to 1 plus 2t plus t square. I have stated it earlier, it's 1 plus t to the power minus 1 that is equal to 1 minus t, 1 minus t, then 1 plus minus 1 square into t square. You can write in this fashion, plus the last term is minus 1 to the power n to the power n. You will see that first minus, then plus, then minus, then plus. So for the what term it is minus 1 to the power n. So you can write it as the last term as minus 1 to the power n to the power n. Now just compare and find out the coefficient of t to the power n from this relation. So you will have pn minus 1 is nothing but the coefficient of t to the power n in this series, that is equal to minus 1 to the power n. So pn minus 1 is equal to minus 1 to the power n, and you can write it as pn minus 1 from this relation is equal to 1 minus 1 to the power n, and after that you can multiply these as into 1, and 1 can be written as pn1 is equal to 1 since pn1 is equal to 1. So from this you can write pn of minus 1 is equal to minus 1 to the power n into pn1. Okay. Now further replacing t by minus t in the series, that is in the relation here in the relation here we replace t, or here we replace t by minus t and x by minus x. So what we will have, the genetic function is 1 minus 2xt was here, so 2 into minus x into minus t plus the last term was t square, so minus t square to the minus half, that is equal to n is equal to 0 to infinity. T is replaced by, since t is replaced by minus t, so it will be minus t to the power n, and x is minus x, so pn of minus x. Okay, so this term will remain the same. Okay, and 1 minus 2xt as for the initial consider as the genetic function initially taken. So 1 minus 2xt plus t square, that is equal to n is equal to 0 to infinity. Then you can write t to the minus t to the power n pn of minus x, and this can be written as t to the power n into minus of x to the power n, and it is as usual pn minus x. So from here, and you know that this term is nothing but n is equal to 0 to infinity t to the power n pn x, and that is equal to this n is equal to infinity t to the power n pn minus x minus 1 to the power n. Now if you compare this on both sides, so the coefficient of t to the power n, what you will have pnx that is equal to minus 1 to the power n and pn of minus x. So it is another important relation, and similarly you can you can show that Pn of minus x is equal to minus 1 to the power n Pn of x. Okay, it is not very difficult. It can also be proved. And then come to the recurrence formula for Pn. The recurrence formulas, there are some relations which can be drawn from, which can be carried out from the from different form of Pnx. So in this topic we will find out different relationships using Pnx. So let z as a function, z as 1 minus 2xt plus t squared to the power minus half. That is nothing but n is equal to 0 to infinity t to the power n Pnx. So this is the generating function. Now squaring this term, z square is equal to what will be it will be 1 minus 2xt plus t squared to the power minus 1. Just take these two terms. So so from this you can write that z square into 1 minus 2xt plus t square, that is equal to 1. I write it as equation 1, and z is equal to somewhere in infinity, this as equation 1. Now differentiating equation 2, this equation with respect to t, we have what we have. First 2z and dz by dt, this will be our constant term right here, and then plus z square is constant term, and differentiate this with respect to you will have minus 2t and then plus from the first term minus 2x and then 2t. So 2t, so I write as z square to 2t minus 2x. You can write it in this manner, that is equal to 0. Now write 2z, take 2z as a common term. So from the first term dz by dt into 1 minus 2xt plus t square, and then plus z is z from here will be only z, and 2 is taken from here and here. So here z and here t minus x, that is equal to 0, or d dz of 1 minus 2xt t square plus z into t minus x is equal to 0, since this is nothing, this 2z is not equal to 0. So now from equation 1, as it was written in here, z is equal to this. Just differentiate this equation. You will have with respect to t, you will have from here dz by dt, and from here I will have n equal to 0 to infinity, then differentiate t to the power n, so n into t to the power n minus 1, and then Pnx. Now substituting this value, this dz by dt, as it is equal to this, so substituting this value of dz by dt in this equation, that is means equation number 3. So what you will have, you will have some, the first term is this 1 minus 2xt t square right here, and then n is equal to 0 to infinity n t to the power n minus 1 Pn x right here this, and then the second term plus t minus x is right written here, and z is equal to n minus 0 to infinity to the power n Pn x, that is equal to 0. So from here just simplify it. So n is equal to 0 to infinity, just multiply this term with these terms, all these terms with this term. So what is the first term, that is equal to, you write as is sum over n equal to 0 to infinity. So here from here n into t to the power n minus 1 Pn x, then minus 2, and from here n, then xt. So right here 2n x, then t to the power n minus 1 is from here and t is from here, so t to the power n will be there, and then Pn x plus multiply this term and this term, so n is here, okay, then t to the power n minus 1 plus 2, that means t to the power n plus 1, and then Pn plus from this term, so multiply t with first from this, so t to the power n plus 1, here t to the power n plus 1 Pnx minus x into t to the power n Pnx, that is equal to 0. Now equating, now in this, from this equation, just equating the coefficient of t to the power n minus 1 from both sides, t to the power n minus 1. If you wish to compare, okay, no problem, from the first term, just from the first term, the coefficient of t to the power n minus 1 is n into Pn minus x. Okay, from the next term, since you are here to compare the, you are here to take the coefficient of t to the power n minus 1. So here n should be replaced by n minus 1. So what will be from this term? So 2 into n is replaced by n minus 1, then x, then pn minus 1, pn is here n minus 1 into x. And from this term, since the coefficient should be t to the power n minus 1, so here also n should be replaced by n minus 2. So you will write here n is replaced, since n is replaced by n minus 2, so n minus 2 is here, then pn minus 2 and x. After that, from this term, here also n should be replaced by n minus 2, so you will have pn minus 2 into x. And from this term, straightly you can write here in straight manner that x into pn pn minus 1, because in this case n should be replaced by n minus 1. So we actually get this line to equating the coefficient of t to the n from both sides. That will be zero since the right hand side has nothing. And from this, after doing simplification, you can write, you can find that the first term n into pn minus pn into x. So first term is n into pnx, then minus, if you simplify this, the relation here, 2n minus 1 x pn minus 1, another term is x is pn minus 1. So this is negative sign is taken as common, then it is 2n minus 2, and from here you will have another plus 1. So actually these two terms, if you combine these two terms, so 2 into 2 in, no, there will not be 2, so it will be 2n minus 1. It will be 2n minus 1 x into pn minus 1 into x. I have written here, that is written here, 2n minus 1 to x into pn minus 1. And then for the terms p to n minus 2, here pn minus 2 and here pn minus 2. So it is n minus 2 and 1 will be come from here, so n minus 1 into pn minus 2. So it is written here n minus 1 into pn minus 2 is x is equal to 0. So finally we get the relation npn is equal to 2n minus 1 x pn minus 1 x minus n minus 1 pn minus 2 into x, which is the recurrence formula for pn. Now some important relations which are to be proved from using recurrence relations. First one is that just proof these as npn is equal to n minus 1 pn minus 1 x minus n into n minus 1 pn minus 2 x. If you wish to prove this, actually I have done here it once again. You need not to do it once again, because it has already proved. It has already proved here. It has already proved here. So you can just look at it. But you can employ any one of these two proofs. Okay. So I am leaving this section only. Now come to the second one. Here we are to prove that npn x is equal to x pn prime x minus pn minus 1 prime x. This identity we have to prove. So to do this, we know that generating function is 1 minus 2xt plus t square to the minus half, that is equal to somewhat t to the power n pnx. We know it very well. Now differentiating this equation with respect to t, then we will have these with respect to t, then we will have 1 minus 2xt to the minus 3 by 2 with a negative sign of half, and then differentiating these 2 into t n minus x, that is with n into t to the minus n pnx. So after from this term you have x minus t 1 minus 2xt plus t square to the minus 3 by 2, that is equal to n into t to the power n minus 1 pnx. So differentiating once again equation number 1, that is I have written it as equation number 1 with respect to x. So what we will have, minus half 1 minus 2xt t square to the minus 3 by 2 into minus 2x from minus 2t from here, that is equal to n into t, that is equal to that is equal to, from here, t to the power n pn prime x. So that t to the power n pn prime x. So from here, after doing simplification, t into 1 minus 2xt plus t square to the minus 3 by 2, that is equal to t to the power n pn prime x pn prime x. I have written it as equation number 3. Now just dividing equation 2, that is equation number 2 is here, dividing equation number 2 by equation number 3, equation number 2 by equation number 3. So we have from here this term and this term will cancel out, this term will cancel out, and x minus t by t is here, that is equal to sum over n t to the power n minus 1 pn x by sum over t to the power n pn prime x. So from here, just multiply this two term, x minus t into t to the power n pn prime x, that is equal to t into this term, that is equal to n into t to the power n will come out from this term and pn x. So that is equal to, just multiply each term of this by this. So x t to the power n pn prime x minus t n plus 1 will be here pn prime x, that is equal to sum over n t to the power n pn x. Now equating the coefficients of t to the power n from both sides, t to the power n, coefficient of t to the power n from both sides, what we have from the first term, it will be x into pn prime x minus, from here n should be replaced by n minus 1. So from here pn minus 1 prime x will be left here, and that is equal to n into pn of x. So finally we get n px is equal to n pn prime x minus pn minus 1 prime x. It is proved. Then another relation, we wish to prove another identity, which is let that identity will become in the next, after next some lines. So from the identity, we already have computed the identity that n pn x is equal to n minus 1 x pn minus 1 x minus n minus 1 pn minus 2 into x. It was done for the first case very earlier in this topic. So differentiating this with respect to x, so from this we will have n to pn prime x, that is equal to n minus 10 pn minus x. Okay, then x is a common term, so it will be the constant term, then pn minus 1 into x, and from here pn minus 1 prime x minus n minus 1 pn minus 2 prime x, and then from the next term n into pn prime x, that is equal to n minus 1 pn minus 1 x, plus just write this term as, since 2n it can be written as n plus n, so n plus n minus 1, 3 terms is there, so write here n into x pn minus 1 prime x, and the left term in this case is n minus 1, so n minus 1 is written here x pn minus 1 prime x, and then minus n minus 1 pn minus 2 prime x, this. Okay, now just take this term here in this left hand side, so here and from here and here n is a common term, so here will be pn prime x minus x pn minus 1 prime x, that is equal to 2n minus 1, from here 2n minus 1 pn minus 1 x, plus from here n minus 1 x pn minus 1 prime x minus this term is linear multiplier. Okay, next term is n into pn prime x minus, write this as usual, then take this it is okay, no problem, and write this term, just take this term here n minus 1 into x pn prime n minus x, and from these two terms, what is these two terms, this term and this term. So n minus 1 is a common term, and if you change the side, if you take this towards the left hand side, then it will be minus of n minus 1. So the left term, the other terms will be x into pn minus 1 prime x, you write here, and from here with the negative sign pn minus 2 prime x, and that is equal to the residual part, that is 2n minus 1 pn minus 1 into x. I write it that equation number 1. Now from the relation, this relation is also established, that is x into Pn prime x minus Pn minus 1 prime x, that is into nPn. This relation also has also been established. So we have, from this we can write, just replace n by n minus 1 in this relation. So from this term you will have n minus 1 p n minus 1 x, that is equal to x p n minus 1 prime x minus p n minus 2 prime x. Here replacing n by n minus 1. So that is equal to, n is a common term, that is equal to n into, now just look at here, from equation 1, that is equation number 1 is written here. So now from equation number 1 you can write that n into Pn minus x minus n into Pn minus 1 x, that is equal to minus with the minus sign. Just substitute this value. You will have this n minus 1 whole square Pn minus 1 x, that is equal to Pn minus 1 Pn minus x. Just substitute these values in equation number 1. From equation 1 we can get this. So now we just simplify n into Pn prime x minus x into Pn minus 1 prime x, that is equal to, just simplify this n minus 1 square to n minus 1 Pn minus 1 x. So the complete calculations is given here. Just look at it, and it will be not very difficult to understand. So finally we get Pn prime x is minus x, Pn minus 1 prime x is equal to n. Just I have skipped some lines to discuss, but if you practice it or if you carefully see it, you will understand. So we have the recurrence relations as n x is equal to n minus 1, this, and okay, this is a recurrence relation which we actually already found. Now in these recurrence relations, replace n by n plus 1. So what we have, you will have this line. Just practice it. It will be not very difficult. So just practice it. Replace n by n plus 1. You will have this line. Then you can write this term n plus 1 Pn plus 1 is equal to this, as this, and differentiating the above relation with respect to x, you will have this then. Just practice it, and all the steps are written here. Just practice it. And finally we will get x Pn prime x minus Pn prime n minus 1 x, that is equal to n into Pn x, and from this you can write Px into Pn prime x is equal to n Pn x plus Pn minus 1 x. Plus can shift this to the right hand side. So this is another relation. This we have obtained this, and then using relation of x Pn prime x in equation 1. So you write what is equation 1. This is the equation 1, and in this equation 1, just you use the value of x Pn prime x from this relation, and if you, that means this term is substituted in equation 1. If you use that, then you will have n plus 1 Pn plus 1 prime x is equal to these. Just simplify it. All the steps are written here, and then the next line is equal to this, and finally we will have to n plus 1 Pn plus 1 x, that is equal to n plus 1 prime x minus Pn minus 1 x. So in this case it is not very difficult. I said it repeatedly that all the steps are derived here. Just you practice it, and you will have no problem to understand this. Okay, and today the last one is there is a problem. We wish to solve it, and here it is written that starting from the generating functions for Legendre polynomials, prove that p2n of 0 that is equal to minus 1 to the power n into 1, 3, 5, 2n minus 1, 2, 4, 6, etc. 2n. We have to prove it. To prove it, you write here the generating function Legendre polynomial is of Legendre polynomial is as that n is equal to 0 to infinity is equal to 1 minus 2x t plus t square to the minus half, and you write x equal to 0 in this relation. You have n is equal to 0 to infinity t to the power n pn of 0 that is equal to, if you use x equal to 0, then you will have 1 plus t to the power minus half. So from here n is equal to 0 to infinity t to the power 2n, just in this case replace n by 2n in this relation. So t to the 2n, 2n of p2n of 0 that is equal to 1 plus t square to the power minus half. Now if you expand this in series, you will have 1 minus half t square plus half into 3 by 4 t to the power 4 minus plus 135. In this fashion the last term will be 2n minus 1, and in the numerator and in this case the last term will be 2n, and here 2 to the power 2n is also written here. So the last term will be this. So now just equate the coefficient of t to the 2n from both sides. You will have p2n here. From here the coefficient t to the 2n is p2n of 0 that is equal to, from here 1, 3, 5, etc. the last term 2n minus 1, and 2, 4, 6 the last term is 2n. So it is written here. So now what was the problem? The problem was this p2n is equal to this. So it has, just here you should remember that here minus, then plus, then minus, then plus. So the last term will be here minus 1 to the power n. So here there is another term minus 1 to the power n. Just rectify it, minus 1 to the power n, and this, and here also minus 1 to the power n should be there. Okay, so just practice all these and there will be no problem to understand. And here I am just, this is the end of this lecture, and you should just practice all these things and there will be no problem to understand.